Hi. In this first video of mine, I'm going to show the proof that the derivative of x to the n is equal to n x to the n minus 1, and we're going to do so by using induction and the product rules. Okay. First, to begin, we're gonna let x be in as any whole number n. And we're going to start by taking the derivative of x to the first power. So if you take the derivative of x to the first power, we know that it's going to be 1. But it also means that this expression can also express the derivative of x to the first power right here. 1 multiplied by x to the 1 minus 1, which is the same thing as 1. But here we can see that this expression is also equivalent to this expression right here, which we have n as 1 and n minus 1 is right here. So now we can see that it holds for n's equal 1. So we're gonna let n's equal k, any number k. So from this we know that it's true for n equal k, proving that this derivative. And now if we can see that if it's true for n equal k plus 1, then we will finish our proof. So now let us take the derivative of x equal k plus 1. So that would be equal to the derivative of x multiplied by x to the k, because it's xk plus 1 and x has a power 1 right here. When they add up, you get to k plus 1. So that equal to that. And now we're going to use the product rule, since they're products right here. And the product rule said derivative of f of g is equal to f g prime plus f prime g. So we're going to have x, derivative of x to the k, plus derivative of x plus x to the k. And now let's do some simplification. We get x back, and the derivative of x to the k is just k x to the k minus 1, plus the derivative of x is just 1, and we get k x to the k back. And right here, some people might confuse, I know I did the first time, that this is what we're trying to prove. So how come we're using it in this expression right here? Well, if you look back, we already we already established that the derivative of x to the k is equal to k x to the k minus 1 right here. And we also says that n is equal k. So we already established that this expression's already been proven. But now we're trying to prove that if this is also true for k plus 1. If it does, then we finish with our proof. So this is what we got. And if we simplify this expression right here, we're going to get this expression right here, because this is x to the power 1. So x to the power 1 multiplied by x to the k minus 1. Minus 1 plus 1 cancel each other out. We get k x to the k power plus x to the k power right here. And now we're going to take, we're going to factor out x to the k power, and we're going to get left off with k plus 1. And it might not look like we are finished, but we are, because if we can see right here that k plus 1 represent n, which we established earlier. So if this is true, it would follow n x to the n minus 1. So n is the k, and k plus 1, okay, n minus 1. So n minus 1 would be, okay, let's erase that out. N equal k plus 1. So n minus 1 is equal to k plus 1. We're trying to find n. It's equal to, oops, that doesn't cancel out. Okay. K plus 1. No, oh, never mind. No. Oh, okay. Alright, my apology. Oops. Let me rewind back. So, okay, we have n equal k plus 1. So, k would equal to n minus 1, which we have here. K, n minus 1. And we're done with our proof by using induction and product rules to prove that derivative of x to the n is equal to n x to the n minus 1.